Welcome back, everybody, to our course on memory device technology for AI/ML computing. I'm your instructor Shubhadev from IIT Hyderabad. Today, we have reached the final lecture of our course, and here we will focus on analog in memory computing. Before we begin, let's do a brief recap of what we discussed in the previous class. Remember, in the last class, we started with the core motivation behind in-memory computing, that is to reduce the data movement between logic and memory, which essentially dominates both energy consumption and latency in data-driven workloads. And this becomes even more stark when you run these data-driven workloads under the traditional von Neumann architectures. We saw that for most modern AI applications, the cost of moving data back and forth is often much higher than the cost of computation itself. We also discussed previously how true neuromorphic computing, while having a lot of promise for energy efficient computing, requires significant redesign at the level of devices, circuits, and architectures. The promise of in-memory computing is that we will try to achieve the same energy efficiency by performing logic and arithmetic operations within the memory fabric itself, while making very small changes or minimal changes to existing memory architectures and technologies. Before we moved to true in-memory computing, we examined a more immediate deployable solution. Remember, it was near memory computing or process in memory architectures. Through several examples, such as the HBM PIM from Samsung and Tensor DIMMs, we saw how bringing compute units physically close to memory can already provide substantial gains by reducing this data shuttling back and forth. Then we introduce the two main paradigms, as you can see on the slide, of digital and analog in memory computing. The key distinction here was that while digital IMC uses conventional SRAM and DRAM, which implements Boolean logic, offering very high precision and robustness, analog in-memory computing relies on multiple non-volatile resistance states to achieve much higher density and energy efficiency, but it has its own set of challenges that we will be discussing today. Using concrete examples, we saw in the case of digital in-memory computing, how activation of simultaneous word lines, both in DRAM and SRAM, enables all these Boolean logic operations directly inside the memory. We also looked at a specialized case, remember, of doing partially analog vector matrix multiplication with digitally stored weights using the SRAM based structures. And this is what will slowly enable your mixed signal MAC operations. With this foundation in place, let us now begin as we conclude the course by turning our attention to specifically analog in memory computing. What are its architectures, what are its advantages, and what are its key challenges and opportunities going forward that need to be addressed to make it practical for future AI systems. So let us understand first the fundamental building block of analog in-memory computing, which you see right over here. So here the memory cell which I have shown is not a cell which just stores a binary 0 or 1. Instead, it stores a conductance value that I have indicated with the value G. And it's not just a simple conductance value, it is a variable conductance value. Means you can gradually tune the conductance of this particular resistor to represent multiple non-volatile resistor states. And that is what is at the core of analog in-memory computing. So to this tunable conductance, when we apply a analog voltage Vin, is converted from a digital source using a D2A converter, because as we will see that although the main acceleration part of analog in-memory computing happens in the analog domain, the signal transmission to and from other parts of the chip happens in the more reliable digital domain. So this digital data needs to be converted into analog data. So this is what this D to A converter does. And this is passed through this variable conductance. So the key idea is very, very simple. Larger the conductance, the larger is the current for the same input voltage. So in a single device, what we are essentially doing is nothing but Ohm's law. The output current of this contraption, when you apply an analog voltage to an analog conductance state, the output current that you get is the multiplication between V in, which is the voltage, and the conductance G. If you have been following this course very well, you can easily guess what could be an ideal system to implement these variable conductances. We have discussed in ad nauseum detail that these variable conductance states could be your multi-bit electronic non-volatile memories, and the way to tune the conductance of these conductance states is through these potentiation and depression measurements. I will not go into details because we have covered them when we were covering ENVMs and also synaptic applications of ENVMs in the last two sections. So this is one simple element of your analog in-memory computing where it is performing the multiplicative action. Next, let's move to having two such elements in series. So let us see what is happening over here. So here we have two different conductance G1 and G2 through which you are passing different input analog voltages, which is V in 1 and V in 2. So at the end of this node, the output of your first conductance device will give you I out 1, which will be equal to V in 1 multiplied by G1. Whereas I out 2 will give you the value of V into G2. Now what happens at this particular output node? Because they are connected in series, the total current by the virtue of Kirchhoff's current law will be that both these currents I1 and I2 belonging to these two separate branches, branch 1 and branch 2, when they are connected together, they will just be summed up. So I total will be equal to I1 plus I2, since I1 is equal to G1 multiplied by V1 and I2 is equal to G2 multiplied by V2. The total I1 will be G1 V1 plus G2 V2. Now I hope you are able to see what is happening over here. Just by using basic laws of physics, we have two operations which are happening naturally and in parallel. Each and every memory element performs a multiply operation, whereas the array wiring performs the addition operation. So in conclusion, this is exactly what we want for deep neural networks, which is the multiply and accumulate operation, which is the core of all that is happening at every node of a neural network. So the key takeaway from this particular demonstration is that analog in-memory computing does not compute using logic gates. Instead, it computes exploiting device physics, which is the multiple conductance states of ENVMs and simple Kirchhoff's law and Ohm's law. And with these basic physical laws of nature, you are able to perform a multiply and accumulate operation. Now let's scale up these two elements into a two-dimensional array of conductance matrix. So here in the two-dimensional array, you have G11, G12, a row of conductances and a column of conductances, and at each and every row, you are applying the voltage V0, V1 right up till Vn. And what happens at the end of every row, you get a current I1, I2, Ij, and then In. So each and every input which is applied on the row will get multiplied by that particular element, and the summation will happen at the end of each row. If you think very carefully, you will know that the jth current or the current at the jth column will be nothing but the summation of the individual row input voltages multiplied by the corresponding conductance which is there in that particular cell. And this is exactly what is vector matrix multiplication. To make things very clear of how this is useful in case of an deep neural network, let's do a direct one-to-one correlation. So all this vector matrix multiplication that was possible through this 2D matrix of conductive elements through the application of Ohm's and Kirchhoff's law is that all these particular conductance states are now a proxy for weights. They are a proxy for the synaptic weights which are getting multiplied by the corresponding inputs V0, V1 and Vn. So the part that I have marked out, or one branch or one column of this 2D array matrix, will give you the multiply and accumulate operation for one of the nodes of a neural network. Now, why is this very important? This is important. We have studied this in detail, that if you look at the most energy and latency expensive operation of any neural networks, and this is some data I have taken from IBM research, this has different relative percentages of power consumption for different operations within the neural network. You will see that the most expensive operation is always the VMM or the MAC operation. So now let's pause and compare this way of doing vector matrix multiplication with the digital computing. In a conventional digital processor, computing of VMM of size n cross n requires n squared multiply and accumulate operations, which are executed sequentially, or sometimes they can also be done partially in a parallel fashion with several and repeated memory access. And that means that the computational complexity of the problem scales as O n squared. So for those who are not very aware of what is the meaning of complexity, it is a term which is coming from theory of computation. What you essentially look at is, as my inputs scale from 0, 1 to n, how many steps do I need to perform that algorithm or that operation? But as we have seen in this slide, the complexity of the same vector matrix multiplication becomes a one-step process when you do vector matrix multiplication using analog in-memory computing. And because MACs are the dominant operation in AI, going from n squared complexity of digital operation to a single physical operation in analog in-memory computing has this great promise of giving you orders of magnitude better gains in energy efficiency and also in throughput, especially for very large neural networks. So the near-term focus in analog in-memory computing is to have inference engines where you train the deep neural network offline and you load these trained weights onto this 2D matrix and simply do inference. So this inference engine, what we saw in IBM's True North. However, the long-term goal is also to do online training through continuous tuning of weights, both in supervised or unsupervised manner. So this is the key focus or goal of analog in-memory computing. However, it has its own set of challenges. The device challenges is something that we have dealt in detail, so I will not again brood about it, but the key device challenges still remain in the non-linearity of weight update. That is, that because the operation of these eNVMs is inherently nonlinear, when you start applying similar pulses, the weight update is not always linear. And as we have discussed, there are different ways to deal with this problem, and one of the ways is to have intelligent non-identical pulsing, which brings your non-linearity, as you see in the orange curve in A, to something which looks like very linear in case of C. The second important problem that we deal with in these eNVM arrays is large amount of cycle to cycle and device to device variability. This also we have spoken in detail when we were covering eNVMs, and we also saw how by using different techniques such as write and verify, you can somehow control this cycle to cycle and device to device variability with improvements in your peripheral circuitry and also software infrastructure. So now that we have quickly touched upon the challenges at the device level, which are the same as any problems in eNVMs, let's look at the challenges at the peripherals or the array peripherals. This is because a significant portion of the complexity, and as we will see, the energy cost actually comes from the peripheral circuitry that surrounds this analog memory array. So let's break this down. On the input side, as you can see, the analog in-memory computing requires digital to analog converters to convert digital data into analog voltages or currents that the array can process. Now, if you try to improve the precision of this DACs, naturally the area and power consumption will increase. These DACs must be reasonably linear and precise, especially when we want more than 3 to 4 bits of effective accuracy. Unfortunately, DACs can consume a lot of energy per conversion, often dominating the total power, especially when your array sizes are very, very small. At the other end is your analog to digital converters. This is absolutely essential because after the current accumulation which happens at each and every column, this analog current requires an analog to digital converter, and this also is typically the major bottleneck in analog in-memory computing. Higher the resolution of these ADCs, 8 bits or more, they consume disproportionately higher energy and area. Even a 6-bit ADC can consume orders of magnitude more energy than the analog computation itself. And this becomes a very big issue and very big challenge as the array sizes starts increasing or you need higher and higher precision. And it has been now shown that the fraction of power that is consumed in analog vector matrix multiplication, only a small fraction, only 10 to 20% actually is from this actual vector matrix multiplication. Rest, most of the power, 80 to 90%, is consumed by the analog peripheral circuitry itself. So there is a lot of work which is happening in trying to see how we can mitigate these effects. Next, we move on to the chip level implementation of analog in-memory computing. So far, we have looked at a single analog in-memory computing tile and see how it very nicely performs a vector matrix multiplication just in one step. But still a main question remains, that is, how do we use this basic building block to accelerate an entire deep neural network? Remember, a deep neural network may require several dozens or even hundreds of such vector matrix multiplication operations, all done layer by layer. And this is where system level or chip level architecture becomes absolutely crucial. And this is the way to go forward. What we essentially need is a way to make several of these analog in-memory computing tiles or arrays, each performing one vector matrix multiplication, and connect them into a flexible and programmable which can execute a complete model. And the solution to do that is by using mixed signal network on chip architecture. We are familiar with network on chip architecture as we were looking even at NOC based architectures which were used in IBM Loihi North, where individual accelerating elements like the synaptic cores were put together in an array and communication was facilitated through your network on chip. So what is the key advantages of this tile to tile communication? Here the data which is in digital form is exchanged via this network on chip, and this allows you to have a scalability to larger models by doing a layer by layer execution of deep neural networks. And this pipelined form of computation really helps in achieving scalability to large models. However, the key concept here to understand here is that the bandwidth requirements of NOC is very, very low. Why is this the case? Because most of the heavy computation is happening within these analog tiles itself, and only sparse data movements is happening within these tiles. Therefore, you do not suffer from the usual von Neumann bottleneck. Finally, an important point to note is that all of this mixed signal hardware requires programmability and coordination, which is generally handled by a lightweight global controller. This can be a simple RISC processor, and this controller orchestrates the entire DNN execution. It schedules the in-memory computations, it configures the ADC precision and also the sensing modes. And it does it dynamically so that a good balance can be reached between the accuracy of computation and also the power consumption. And this kind of architecture gives you a very versatile and programmable hardware platform where you can do both training and inference. So with this understanding, let us go and see some of the implementations of both digital and analog in-memory computing in actual hardware. So this work, which was published in ISSCC in 2020 by TSMC, is a great example of digital in-memory computing, implementing a highly optimized 80 SRAM based compute in memory macro using a standard 7 nanometer FinFET technology. The choice of 80 SRAM cells over the conventional 60 SRAM cell. Remember why 80 was preferred? Because of larger noise margins. And these noise margins are very important to allow for the multiple word line activation so that there is no read disturb which flips the bits in the cell. And this macro, which they had shown, performs 64 parallel 4-bit by 4-bit multiply and accumulate operations per cycle with 16 input neurons, as you can see over here. So during the operation, the right bit line is pre-charged and multiple row activations are done, as we have seen, which discharges the bit line depending on the stored bits, and each computation capacitor samples the bit line. A post-sampling charge sense step among the binary weighted capacitor produces the final analog MAC level, which is digitized by a 4-bit flash ADC. And with this, the authors explicitly model device-to-device nonlinearity using better neural network training, improving the MNIST accuracy by almost 30%, and it shows very good convergence to software levels just with 4-bit precision. This was fabricated, remember, in the 7 nanometer node, and the 64x64 macro occupies a very tiny space and is able to achieve the entire compute in memory cycle just within 5.5 nanoseconds with 0.4 volts with a very impressive tops per watt of roughly 350 tops per watt energy efficiency. So with this, let us move on and look at some implementation of analog in-memory computing using phase change memories, which are used to perform massive parallel matrix vector multiplications directly inside the memory array, which consists of 1T 1R cells, where this 1R is the PC RAM. The main reason for the success of this PC RAM based AIMC design, which was shown by IBM, was the ability to tune multiple level conductance states, where these states encode analog weights, which enable high density and very fine grained weight representation, which is absolutely necessary for neural network inference with decent precision. However, the PC RAM devices, as we have studied, exhibit lot of non-idealities such as conductance drift over time and non-linearity in the weight operation. And what this work does is it addresses all these challenges through peripheral compensation techniques, such as having reference conductance states, write and verify, and even adaptations to the readout circuitry. So these circuit level innovations maintain very high multiply and accumulate accuracies, even though the constituting devices are inherently suffering from lot of non-idealities. And because this computation is analog and massively parallel across these different crossbars, the overall energy and data movement overhead is dramatically reduced, because the PC RAM array not only is storing the weights with multiple level analog precision, but it is also performing the bulk of the computation inside the memory itself. And this demonstrates one of the first real life practical hardware implementations of analog in memory computing as a solution using a matured non-volatile memory technology. So we conclude our discussion by looking at the stellar work from Stanford University, where we look at this chip called the NEU, New RAM, which is a landmark example of doing analog in-memory computing that works not just at the device level, but through several layers of co-optimization across different multiple hierarchies, from devices and circuits all the way up to algorithms and system software. I really encourage you to read this particular paper that I have marked out for you in order to understand the true complexity and true nature of challenges that they have overcome to do a great design in analog in-memory computing. So before we go into the sub-blocks, let me very clearly articulate what is the meaning of co-optimization. Co-optimization means that instead of designing devices, circuits, architectures, and algorithms all done independently, they are all designed together with constraints and capabilities at one level, explicitly shaping decisions and modulating decisions at different levels. So first, let's focus on how they manage to transform a software neural network into hardware. And this was done by having NeuRAM as a 48-core analog in-memory computing chip, where each of the core consists of a transposable neurosynaptic array, which is capable of doing analog vector matrix multiplications. As shown in this diagram, the neural network is first partitioned layer by layer, and instead of mapping the entire network into a single large array, what NeuRAM does is it distributes different layers or part of layers across different multiple cores. Remember, each core consists of this TNSA array, which can individually do vector matrix multiplication. And the key advantage of doing this is that the corresponding synaptic weights, which are locally doing the analog vector matrix calculations, can all work in parallel. And these results are then routed digitally between the cores to form the next layer's inputs. And this core level parallelism is what allows NeuRAM to scale to larger networks while keeping data movement very, very limited. The next level of abstraction we will look at is the transposable neurosynaptic array, which is doing the vector matrix multiplication itself. So as you can see, here we have your transposable neurosynaptic array, each consisting of 256 cross 256 CMOS neurons and consequently RAM cells, which are at the cross point of each and every neuron. Now let's understand what is transposable in this neurosynaptic array. It means that this array can be dynamically reconfigured to operate either in the row-wise or column-wise mode. This transposability is absolutely crucial because it allows the same hardware to operate under the forward inference and backward weight update which is necessary in training. In other words, this architectural flexibility of this TNSA core allows algorithmic flexibility to have inference and training within the same chip. And this is why this was a very big breakthrough. Next, we look at the optimizations at the circuit level and the system level. As we can see in the diagram, the authors have done a series of co-optimization both at circuit and system level. The new RRAM uses carefully designed peripheral circuitry such as current mode and voltage mode sensing with adaptive reference levels and controlled programming pulses. All of this is done to do what? To mitigate the non-idealities like non-linearity and cycle-to-cycle variability that comes as a part of your RRAM devices. Some of these challenges are essentially handled through program and verify schemes, while others are absorbed into system-level scheduling and data flow. And all of these innovations improve the accuracy, but there is a cost of increased peripheral complexity. And this highlights that there is an important trade-off in analog in-memory computing. The final thing that we will look at is that because of this really flexible design, the new RRAM chip is able to perform end-to-end validation on real-life workloads. And this they are able to achieve with competitive accuracy across several different tasks, as you can see here, whether it is MNIST classification, ResNet task, or even LSTM tasks. The key takeaway here is that good perform is not achieved only by perfect algorithms or perfect devices or by perfect circuits, but through the coordinated design or co-optimization across software, architecture, circuits, and devices. And this is the closing takeaway from our course. Although we were primarily focused on memory device technology and its applications in AI/ML computing, it is important to know that modern computing relies on several things from algorithms, device design, circuits, and systems all coming together to give you the optimal performance. And this is the beauty of this very interdisciplinary field. With this, let us conclude the technical portion of our course, and in a small lecture which will follow, we will look at a brief recap of whatever we studied along with future challenges in this great bid to enable scalable and energy efficient hardware for AI. Thank you very much for your attention and taking this amazing journey with all of us.